So let's keep learning about how to calculate this perspective view frustum. So perspective view frustum part 2, the sequel. Scaling -1 to 1. And this gets a little ugly. The derivation gets a little ugly, but I think the idea should be simple. We've already done this for orthographic. You rescale to 2, you shift, you divide, it's all good, right? But I'm going to spell it out for us anyway, because I think it's really useful to see how that works. So here's my I over here. Let's see if I can do a good job of this. Here we go. An artist I am not. Yay. Okay. Oops. So, that was a mistake. Okay. So I made this view frustum again. And I was about to make this exact same mistake. So here's my view frustum. And, okay, well, I'll fix that. Remember, this is my far here, this is my near. This is my bottom, top, my right, my left. Anyway, wait a second, that's backwards, Jim. Yeah, looking from the eye, that's the right, and that's the left, okay? Now, the first thing I want to highlight is that our division by Z that we do in the previous step, it changes it from a frustum into a square or a rectangular prism. Paletoped, that thing I dropped, that thing about, makes it into a rectangular prism. Okay, that part of the transformation already gives us this kind of shape. Okay, it takes the Z at the far, it squishes it in. The division by Z just brings everything in. The further away it is, the more it gets squished in. So after we divide by Z, we're basically into an orthographic projection. We collapse the depth. So let's look at how that works without breaking the things we've already done. So I'm going to draw a point on this canvas here. This is a point in our image plane, of course. This is what we're trying to solve. So that point is going to be X on the screen, Y on the screen, and then also let's put Z on the screen in there, just because. So I'm going to write out a little equation for you. Left is less than or equal to X on the screen, which is less than or equal to right on the screen. Is that right? Okay. This is kind of what we want, right? We want it so that, all right, let's solve for X of S so that, was what we have, I'm sorry. X of S is definitely within left and right. So I set this up, this is a true equation. Now what I want to do is do algebra, rework this so it's -1 on the left side, +1 on the right side, and then I'll have my equation of how to solve for that. And the same thing goes for the Y. The Y, the screen coordinate, is bigger than my bottom, which is less than or equal to the top, okay? So we have these two equations, pretty simple. But let's work through this one here first. So the first thing I want to do is I want to offset it to 0. So what I can do is, if I subtract L from both sides, I'm rescaling this to go from 0 to width. So I'm going to minus L from both sides. Minus L, minus L. So L minus L is 0. I shouldn't say both sides, all three pieces. X screen minus L, which is less than or equal to R minus L. Cool. Now I'll make a comment for myself here. So now we go from 0 to R minus L, which happens to be our width. Right? Cool. So we've rescaled. So if I want to go from 0 to R minus L, I do X of S minus L. Cool. Now I want to start normalizing this to length 1. So I'm going to, maybe I'll use green for this. I'm going to now divide by R minus L everything. So 0 stays 0, which is nice. Then I have X of S minus L over R minus L. which is less than or equal to 1. Awesome. So now if I want to scale my whole equation from 0 to 1, I just plug in x of screen minus left over right minus left, and now I have 0 to 1. Of course, we don't want 0 to 1. We want 0 to 2, right? So then I can move it from -1 to +1. I want a 2 by 2 canvas to be normalized device coordinates. So to do that, I multiply everything by 2. And of course, 0 multiplied by 2 stays to be 0. So I have 2 xs minus L over right minus L, which is less than or equal to 2. Awesome. So now I have 0 to 2. But of course, I want -1 to 1. And you should see how that can go. I just subtract 1 from both sides. All sides. So we have -1, which is less than or equal to 2xs minus L over right minus L minus 1, which is less than or equal to 1. All right, so we've done it. If I want to take our point x of s and transform it so I get a normalized coordinate from -1 to 1, I just go 2 times x of s minus L over r minus L. This is now -1, 1. Now, this is not what we actually end up using. There's 2 multiplications in here, or there's subtraction and a multiplication. It turns out to be there's a different form that's a little more preferred for various reasons in the OpenGL matrix. So you might look at this, go online, look at the OpenGL matrix, and go, it looks different, Jim. So I think I'd like to just finish up this derivation, just a bit of algebra to put it into its preferred form. Okay, let's go to the preferred form that you'll see online. So the first thing I'm going to do is I'm going to convert this 1 here to a fraction so I can combine them. This is a trick you should have learned in high school. So 2 of xs minus L over, I should put this in here, -1 less than or equal to r minus L. Now this -1, I'm going to change it to just r minus L, r plus L rather, over r plus L. And that, at this point, scratch that, r minus L over r minus L. I don't know why I said that. Got confused. Okay, which is less than or equal to 1. Now, this is just messy algebra at this point. I'm going to just combine those so I get -1 less than or equal to 2xs minus 2L plus that 1L, so that becomes minus L, and then I have a minus R, right, all over R minus L, which is less than or equal to 1, and this I can rewrite as -1. Bored yet? And I'm going to just do it in this form, R minus L, like that. Is there a mistake? It's an R plus L. Yeah, it's an R plus L. All over R minus L, which is less than or equal to 1. Whew. And this is the form that will help us get it easier into our matrix. So we have -1 less than or equal to 2 of xs over r minus L minus r plus L over r minus L less than or equal to +1. That's a negative. Good. Okay, so this is kind of boring. At first, the derivation should make sense. The rest of it is just algebra to get it into a different form. It just makes things a little easier a little later. Now, if I have my point on the screen, my x on the screen, I can convert it to my normalized device coordinates by doing this. Now, of course, this takes 2 steps. To go from my point x in the world to my point x in the screen, I have to, first divide by z and do all that kind of stuff. So I'll remind you that x on the screen is actually equal to n times x in the window coordinates over minus zw. And this is something we covered a little earlier. Where are we? Here we go, right? So x of screen coordinate right there. I should probably put that in blue or something. It's n times the world coordinate divided by the z. So we've already done that. Let's just make one equation. So I'm going to substitute that back in. and then we're ready to have one equation which goes from a world coordinate, divides by the z, does everything we want, and comes into our normalized device coordinates. Okay. So then this is it. We're done our messy algebra. It's 2 of xw times n over minus zw of r minus l. And all I've done here is I've taken this 2xs. This xs goes here, and the z goes into the bottom, right? Just like that. Minus r plus l over r minus l. Less than equal negative 1, plus 1. My slides all say negative 1, but obviously that's wrong, my notes. So now what we can do is we can convert this into our matrix. And I'm going to start by filling out the pieces we already know. X world, Y world, Z world 1. Like this. Maybe I'll start this way. Yeah. So this is where, if you're not good at your matrix multiplication, it can get a little tricky. But if I want to get this from my matrix form, this is xw, which is here. So I want to multiply xw by 2n divided by r. So 2n here over r minus l. I'll multiply that by the x, and I'll get what I have there. Now this z, of course, you might be thinking, wait a second, Jim. What's going to happen with this z? Well, we already get that z in our equation if I fill in the bottom here, 0, 0, minus 1, 0. We already have that filled in, right? So we can worry about dividing by that z later. It's already taken care of. We're already dividing our x by z with that bottom row. So now let's, in case I've confused you too much, let's work through this. X is going to be 2n times xw over r minus l, right? And then at the end, I'm going to divide by my negative zw. So I've actually reproduced the first part of this one right here. Okay. So I've reproduced that first part. Cool. So that'll give me my coordinate. But I'm missing a part. I'm missing this thing right there. So what I do is, trust me for a second, we don't use y. But what we do is, in the z spot, we put an r plus l over r minus l. And you're like, but it should be a minus, Jim. Yeah, I know. We're going to divide by a z, Jim. Yeah, I know. Don't worry about it. Let's work through it. Okay, so the top one is 2n times xw over r minus l, and then we're going to divide by the negative z later, plus 0y, good, and then plus, okay, r plus l over r minus l times zw, right? But we divide everything by minus zw, so that goes away, and it will become a minus. Oh, okay. So I'm going to rewrite this a little more neatly. This becomes 2n xw over r minus l zw minus r plus l over r minus l. And this is our equation from here. So this is messy, but I want you to understand what's going on. Step through it, work through it, understand where the derivation comes from. You don't need to look at this and go, oh yeah, that's obvious. Nobody knows what's going on. It's all algebra. R plus L over R minus L, right? It's weird. But I want to show you that the OpenGL Frustum matrix that we have, that's common online, it's in all the textbooks, it's not just random. It didn't just come out of nowhere. Where are we? So we can reproduce it. Now this trick of going, I can solve it algebraically, this last part I mean, where I can solve it algebraically, but then how do I do it in matrix multiplication? Now that is tricky, and that is not intuitive. Sometimes you have to really rework things into the right form just to get things to work. This is where this comes in. I'm just telling you what the form is, and you should be able to work through it and go, oh, now I see. That's a really clever way to do it. Now for the y, we just do the same thing, except we put the x of 0 2n over, instead of right minus left, we do top minus bottom, and then we put a 0 for the, for the x coordinate, and then the same thing goes here. Instead of right and left for y, we use top and bottom. Top plus bottom over top minus bottom. We put a 0 there. And I'm going to leave the z coordinates empty for now. Okay. So I don't need to rederive all of this for the y. It works identically the same. But let's just quickly work through that multiplication. Okay. So for the y coordinate, I have 0 times xw plus 2n times yw over t minus b plus t plus b over t minus b times zw. They both get divided by negative zw. They both get divided by negative zw. This goes away. And this is the x coordinate. The y coordinate is going to be 2n times yw over t minus b times negative, I should put a negative zw in the front, I guess, because it should be negative, minus top plus bottom over top minus bottom. So that's it. At this point in time, this is an exercise, a mental exercise to make you confident you know where things come from and you can derive it and you can work through it. But you're not expected to memorize the intuition, but just trust when you look at those calculations, go, yeah, that's just rescaling -1 to 1 and dividing by the z all in one go. So if I just, like many textbooks did, just showed you this and said, yep, trust me, this works, it's magic. But it's not magic, it's just funny algebra, right? This is just funny algebra. Apart from this z line that's still missing, you now know why this Frustum calculation works. And now the result from this, which is really cool, is the x and y are perspective corrected, which means divided by z, and they go from -1 to 1. We have a normalized device coordinates for any view Frustum, okay, in perspective. Cool, let's stop there.